Okay, so we have, I think, so I propose to give like a longer lecture, which is made of two parts. So maybe we'll have a very short break in the middle. If you would like, it's going to be like about an hour and a half. And again, I'm not sure. So yes, again, just feel free to let me know if this is interesting or not. Okay, so as was mentioned, I'm affiliated with Bar-Ilan University. So Bar-Ilan is in Israel. Here you see a map. We are actually quite close to the city of Tel Aviv, which is the main, one of the biggest cities, I mean, the biggest city in Israel. Another known city is Jerusalem, which is, of course, the capital. But Tel Aviv is like more a modern city. And yeah, you can see this is a picture of our campus. It's pretty nice campus, green, etc. And we have about 20,000 students and more than 1,000 faculty members. So we are one of the major universities in Israel. There are six universities, which are all about the same size, and Bar-Ilan University is one of them. Okay, so my group deals with the dynamics of complex quantum systems. These are some pictures, and I've been lucky to collaborate with several corporate companies, manufacturers of quantum computers. Rigetti was mentioned. I also collaborate with IBM and Microsoft, Amazon, etc. So it's really a very exciting time to do quantum computing. And my group is also part of a larger research hub. It's called Kernel, Quantum Exploration and Research in Noisy Large-Scale Quantum Computers. So essentially, the idea is to try and see what can one do with current state-of-the-art quantum computers. So rather than asking, just theoretical algorithmic questions, really focus on the near-term hardware and see what can be used. And this is also the topic of my lecture today. So yeah, these are the, this is our research hub, which covers 22 professors from 6 universities. We have a lot of activities. Even some of them are online. I'll mention them towards the end. So if you're interested, you're welcome to join us for some online events. Okay, so I would like to start with the part one. So part one is about, in general, about quantum computing. And again, let me know if, maybe some topics were covered by other lectures. So just let me know, then I'll go quicker. Okay, so yeah. Okay. By the way, if some of you have the opportunity to open the camera, I think it will be really nice so that I can sort of see who is following, or at least someone is following. Thanks. So, okay. So quantum computing on the cloud really started 10 years ago. And it was IBM who started. And in the beginning, they had the quantum computer with just 5 qubits. So it was really, really small. And also the fidelity of each gate was really low. I mean, 25% means that every time that you place a gate, you have a 5% error. So, after just a few gates, you already lost your signal. But nowadays, it really developed, and 10 years after, we have many different companies that use different technologies like superconducting circuits, silicon spins, NV centers, trapped ions, cold atoms, and photons. So these are all, they're called modalities or way how to build a quantum computer. There are, of course, in many different countries. These are just a few examples. Maybe there are more. There are definitely more companies, but not all of them offer quantum computing on the cloud. So not all of them allow you to connect from the internet. So these are main examples of companies that allow such a service. And if you will focus on IBM, just as an example, they are now up to more than 100 qubits, and the fidelity is up to 99.8%. So it's both much bigger and also much more precise. And that has happened within just 10 years or so. So where are we standing right now? So essentially, we are in a place that we have access to quantum computers as researchers. And then the question is really, what's next? I mean, how can I use such a computer? So of course, you can ask ChatGPT, it will give you an answer, but then you don't know if this answer is correct or not. So you'd rather maybe ask to the experts. So let me give you my perspective on quantum computing. So I think that when we speak about quantum algorithms, we should really focus on mostly two different directions. One of them is we use a quantum computer to solve a classical problem. So, problems that are unrelated to quantum computers, but the quantum computer is a tool. And the other side is when you actually are trying to solve a quantum problem on using the quantum computer. So when you focus on classical problems, I'm sure you've all heard about the Grover algorithm, which is a search algorithm. So the entire world of optimization is based on the idea that the quantum computer can solve optimization problem or look for optimal solutions very quickly. And yeah, so I'm actually the co-founder of a startup in this field, and maybe if we have time, if you're interested, I can show you at the end some slides about our startup and how we use quantum computers to provide solutions for in the industry sectors. Well, you probably also heard about the Shor algorithm for integer factorization, which is basically a way to break encryption, like RSA. And there are more algorithms. So HHL is one. Actually, Hasidim is a professor at Bar-Ilan University, is a colleague of mine. So that's really cool. And these are all classical problems. That's actually not the focus of my talk today. Today, I would like to actually talk about using quantum computers for solving quantum problems. And in particular, this is relevant to problems that come from chemistry and physics, or broader from quantum information. Okay. And then there is, I think, a third direction, which is a little bit unclear, which is quantum and AI. So, of course, quantum is a buzz, AI is a buzz. So people say, oh, yes, then you can join quantum and AI. But it's not really clear. I mean, what are you trying to do? So I think it is very important, when you think of an algorithm, to clarify what is the problem, the specific problem that you are trying to solve. Okay, so we'll focus today on quantum solving quantum problems. And for the first example that was shown in the literature as a successful implementation of a quantum algorithm on a quantum computer was to simulate random quantum circuit. So I'm referring actually to the experiment by Google in 2019, which was really, I think, a very important milestone for the field. This was also the time where I became interested into quantum computing. And of course, it's a Nature paper. What they were able to do is to perform in 200 seconds a task that would take 10,000 years. So, the task was solved much, much faster than a classical computer. Of course, this is an estimate, right? Because they didn't wait for 10,000 years for the classical computer. But anyway, it was very remarkable. And the reason of this acceleration was really the fact that they were using, let's say, 53 qubits. And 53 qubits, when you think of the Hilbert space, which is the size of the problem that you are solving on a quantum computer, it's a problem that has 2 to the 53 options, right? If you have 53 binary numbers, there are 2 to the power 53 possible implementations. Now, in a classical computer, what that just means is that you have, a register with 53 zeros or ones. So you are in one of 2 to the 53 option, right? Which is quite simple. You just write down 53 zeros and ones, so 0, 0, 1, 1, 1, 1, etc. So that gives you one option, and that's it. And if you want to store it, you just need 53 qubits or 53 bits. That's classically. But in quantum physics, we know that the superposition is possible. So you can be in a superposition of all these possible states. And a superposition is basically characterized by a prefactor. So you have, for each of these 2 to the 53 options, you have a complex numbers that is associated with. So if you just want to store such a state on a classical computer, you'd need 2 to the 53 complex numbers, which is really huge. Yeah, that's it. So now, in fact, a few years after, so 5 years after, in 2024, there was a paper published in the National Science Review, which is shown here. These are the authors. And what they were able to do was actually to improve the classical simulation algorithms, and they were able to to solve the same problem which I haven't mentioned. I'll mention in a moment what is the problem that we're solving, the quantum supremacy, but they were able to solve the same problem 7 times faster. So in a sense, they sort of broke the quantum supremacy, right? The quantum supremacy idea was that the quantum computer can solve the problem much faster than any classical computers, but then by improving classical computers and classical algorithms, the balance was restored. However, I would like to highlight a number, which is these 1,400 GPUs. So as you know, GPUs are these very advanced classical processors, which include a huge number of transistors, right? A GPU itself has billions of transistors. So when you take in the numbers and you say, okay, wait, how many transistors are there in 1,400 GPUs? You'll come up with a huge number, which is 10 to the 14. So the idea is then that, in a sense, a quantum computer with 53 qubits is performing similarly to classical computers with 10 to the 14 transistors. And of course, sure, we have 10 to the 14 transistors, right? We just buy many GPUs, which is great. But what will happen when this number goes up? So what will happen when instead of 53 qubits, you will lose 100 qubits? If this number needs to grow exponentially, then it, of course, would mean that you would need to buy millions of GPUs, which is not anymore possible. So I think that in this paper, while on the one hand is showing the power of classical computers, is also showing the limitation of those systems. Okay, so what was the idea of quantum supremacy? Actually, maybe I can ask a question. So were there lectures on quantum supremacy before or maybe after? Yes, no?
Not yet.
No. Not yet. Okay. Okay, great. So thanks. So I'll give I will give a brief introduction to the quantum supremacy. So what is the idea? So the idea is very simple. What you do, you just take a random circuit. So a random circuit is basically, and the specific random circuit, so what you see here, this is typical for quantum circuits. So in the x-axis, you have time, so from left to right, and the y-axis is the qubits. So here in this example, you have 1, 2, 3, 4, 5 qubits, and then you are applying, m cycles of operations. And each cycle of operation is as follows. So there is a single qubit gate. You see this square root of w, square root of x. These are gates that apply on a single qubit. And they were chosen randomly. So they could be either from a set. They could be either a square root of that. So these are all gates. Doesn't matter, the name of the gates is not very important. These are the specific gates that they were applying. There were a set of, I don't know, maybe 10 or even less gates, and they each time they selected one of these gates randomly. So that's where the randomness comes in. That's the first layer. Then they apply, in the second layer, they apply a 2-qubit gate. So here you see I'm applying, or in the drawing, it's applying a gate between those 2 qubits. Then you apply again single qubits, 2 qubits, single qubits, 2 qubits. So the single qubits are always random, are selected from a random set. The 2-qubit gates are always the same for these circuits. Okay, so then of course it's so here you're seeing only 5. Of course, you have 53 qubits, so not only 5, 53, and they are in a 2-dimensional topology. So it's not just a line. It's a 2-dimensional topology where each qubit is coupled to 1 or 2 other qubits. So then what you do? Okay, great. So what you would like to show is that the state that you have created at the end is similar in the experiment, is as similar as possible to the true quantum state. So at the beginning you have a quantum state 0, 0, 0, all the qubits are 0, and in the end you have a final state. So that state, that's psi theory. Psi theory is the state that you would obtain when you applied all those gates. What you would like to compute is the fidelity of the quantum computer, so the overlap between the psi theory, the one you would obtain for this circuit, which is a very complex quantum state, superposition of these 2 to the 53 states, and the experiment and the state itself. What is the problem? The problem is that, well, first of all, it's very complicated to compute the theoretical state. But let's assume that somehow you could do it. An even larger problem, well, I don't know, maybe as large as possible, as large as problem is how to know what is the state that I created, right? In a classical computer, when you do a calculation and you want to know the result of the calculation, just see the registers. Okay, it's written 0011. That's the answer to my algorithm. But in a quantum computer, what you obtain is a superposition of those states. And you would like to know the entire state. So in principle, if you would like to know this state, you would need to apply what is known as full state tomography, which is terrible. I mean, you would need to repeat this experiment many times to know which state you created. So this is a problem of verificability. You don't know. I mean, you created a quantum circuit, but you don't know if the answer is the one that you would expect or not. So there was an idea, really, I think a very interesting idea, which was to probe the fidelity of the state in a different way. So not by performing tomography, not by checking which state you created, but rather using something called the cross-entropy indicator. So what is the cross-entropy indicator? It's this is the expression. So it's doing the following. You perform your experiment and then you measure. When you measure, you get a string, 0, 0, 1, 1, 1, a string of numbers. Of course, every time, because of the superposition, every time that you measure, you will obtain a different state. So I do an experiment, I measure, I obtain a string. Then what I do, I compute the theoretical probability of obtaining that state. So that's basically the amplitude of that specific outcome in the theoretical state. So it assumes that you can simulate the quantum computer, of course. So that works for quantum computers that are not too big, because if they're too big, that you cannot simulate it. But let's assume you can simulate that. So you do the experiment, you obtain a string, you compute the theoretical probability. Then you repeat the experiment again, and you compute the theoretical probability. And you go on, so on, so forth. Then what will happen is that depending on whether the quantum state that you obtained was equal to the theoretically expected quantum state or not, you will obtain for this number, for this sum, a different number. So it's a number that is a little bit larger if that is actually larger. So it's twice as large if the state that you created is the expected, theoretically expected. So if this overlap between the theory and the experiment is 1, then this XEB will give you 2. Otherwise, it gives you 1, which means that basically the fidelity is just the cross entropy minus 1. So what is the intuition? Why do you get a larger number? Here you get the larger number because if you are extracting, so if you, let's say, take the theoretical state. In the theoretical state, there are the theoretical state is superposition of all possible states with different weights. Now, because of quantum mechanics, most probably you will get those states that have a large overlap, right? If you have a superposition, let's say if you have a superposition of 0, 0, 0, 1, 1, 0, and 1, 1, 4 options with prefactors, alpha, beta, gamma, delta. So if alpha is larger, then most probably you will measure alpha. So that means that this p, which is alpha squared, is usually larger. So you don't equally, when you measure a quantum state, you don't equally probe from all possible superposition. Those that have a larger probability will be probed more. And so that's why these states that have p theory larger will come out more often in the experiment. So that's why the XEB is larger in the case where the state that you are probing is the theoretically expected state. Of course, if in the opposite case, so if you just you just create some random chaotic quantum state that has nothing to do with the theoretical one, then these p's will be just average, and that's this one where this one comes from. Okay, did it make sense? Were you able to follow at least the logic? Okay, so let's assume that this is the case. Good. So there is now a graph which is very important. So in this graph, what is showing you is what is the fidelity, as measured before, of obtaining the correct quantum state as a function of number of qubits. Right? So what you see here are different experiments, different type of experiments, and also a theoretical line. And what is very important is that this line is actually, remember that this is a logarithmic scale. So this graph is linear. So the graph being linear means that we're actually in the case of an exponential decay. So every time that we add one more qubit, of course, when you add more qubit, right, you are adding more gates. This is how it looks like. So these are the qubits, and every time you add the qubit, there are more gates in the circuit. And the overall fidelity is actually given by an approximation, which is shown by here. So something like 0.98 times exponential to the number of gates. That's the formula that you would get by fitting this line. What does that mean? That means that this actually allows us to estimate what is the fidelity of a generic quantum gate by knowing what is the error of just a single gate. So if you create a very complicated circuit with many gates, and you want to know what is the expected fidelity, which, as I will mention in a moment, is very important when you try to run an algorithm on a quantum computer, there is a very easy way to estimate what is the fidelity of the quantum computer. And it's just the fidelity of each gate to the power the number of gates. So you just multiply the fidelity of all the gates. This gives you a good estimate of the fidelity of the entire circuit. Okay, so from the single gate to the entire circuit. So from our experience on running algorithms on quantum computers, we've asked ourselves, what is a typical size of a circuit that I can run on a quantum computer and still get a meaningful result? And the answer is that it really depends on, in particular, I would like to focus on something called the quantum volume. So the quantum volume is the maximal size of a circuit that can be run faithfully on a quantum computer. And in particular, we refer to square circuits. So square circuits are circuits in which the number of qubits and number of layers is the same, right? In principle, these are two different factors. How many qubits you have and how many gates you apply. These are two completely different. But in a square circuit is a circuit in which those two numbers are equal. Then, so that's the definition of a square circuit. Then what you ask yourself, so this is in here, for instance, would be n equals to 4. Then, as we said before, you can estimate the fidelity of this circuit by just taking the fidelity of each gate. So let's say that epsilon is the probability of error of a single gate. So 1 minus epsilon would be the probability of a faithful gate. And you take it to the power n squared over 2. So n squared over 2 is just n squared because it's a square circuit. So if n is the number of qubits, the number of gates is n squared. Well, actually n squared over 2 because these are pairs. So which you can, if epsilon is small, which means that you have very good gates, you can approximate it as 1 minus epsilon n squared over 2. Now, what is the question of the quantum volume? So the quantum volume is you take bigger and bigger circuits until you get to a point that the fidelity goes below 50%, right? Of course, if you have a small circuit, the fidelity is large. And when you enlarge the circuit, the fidelity will go lower and lower until at some point you get 50%. So that's where you stop. This is called the quantum volume. So in our case, we can actually have a formula, which is a very simple formula, but just equating 1 minus epsilon squared over 2. If you take it, you take an identity with, you ask when it is 0.5, you get a number for n. And n is 0.5 divided by epsilon square root. So remember that epsilon is the error, is the mistake, right? So here you see a few numbers. So a typical value for epsilon for a very good, if you have a very good quantum computer, the error could be as low as 0.5%. So an error of 0.1% means that the fidelity is 99.9%. And for this very large number of epsilon, the n that you get is about 20. So which means that you can basically use something of the order of 20 qubits with 20 gates per qubit. So a square circuit of size 20. Later on, I will show you how one can try to increase this number, because of course, this is not a very, we are taking here the data for the best quantum computers, and I'm telling you that you can run at most 20 qubits. So I will show you later how that number can be a little bit improved. But if you just run it vanilla, without doing any error correction, error mitigation. That's the expression. Square root of 0.5 divided by epsilon. So if you take, let's say, this, a very poor quantum computer, which has an epsilon of 1%, then you will see that the number is as low as 5 or 6. So it really becomes slow. The dependency is very strong on the error. But that gives you also an estimate of how large the quantum circuit can be run. Okay. Yeah, great. So remember this number. So let's say that epsilon is 0.2%. So 0.2% is the typical numbers. What you will get is the number of gates. Okay, so the number of gates is n squared. So number of gates is really the the number of gates is just 1 over epsilon, and it's going to be actually 0.5 over 1 over 2 epsilon. It's just 250 gates. So you can, if you have epsilon that is 0.2%, then you can make a circuit of 20, maybe like 15 times 15 qubits and apply 250 gates. Remember this number because it's going to be important later on. Okay, great. So that's where the quantum computing on the cloud is standing. This is an estimate of how large your quantum computer can be. And now let's look at different quantum algorithms. So I have, for simplicity, divided the quantum algorithms in 3 different categories. One in which these are the easiest one is the first one. So the first one, you just give me an algorithm and run it. Let's say I'm doing an optimization problem. You give me, you tell me which circuit I need to run. I run it, I get the result. Great. The option number 2 is algorithms in which you actually need to rerun the quantum circuit many times, or maybe rerun many different quantum circuits, and then post-process them. And the third option is what is known as variational quantum algorithms. So variational quantum algorithms are actually algorithms in which you don't know a priori which quantum circuit you need to run, but you find it on your way. So you run a quantum circuit, get a result, and from that result you will need to change your quantum circuit. So it's a variational quantum circuit. You don't know a priori which quantum circuit will be run. So here are some examples. So examples of quantum algorithms of the simplest type that you just, there is an algorithm like do step 1, step 2, step 3, very easy, like just a classical, like a receipt, right? Very simple algorithm. Would be Grover search algorithm, short factorization, which I mentioned before, and also quantum dynamics. I mean, if you tell me what is your Hamiltonian, what is your quantum systems that you want to simulate, then I just run it on the quantum computer, and that's very easy. Now, quantum circuits that needs to be run many times include random quantum sampling, so the random circuits that I mentioned before by Google, right? You don't know, often you need to average over many circuits. So that's where you need to run many quantum circuits. All algorithms that are based on quantum error correction and quantum and error mitigation, which I'll mention a little bit later, these are circuits that somehow in which you post-process the data over many quantum circuits. In particular, error mitigation is such a technique. So you trying to improve your fidelity by running many circuits and post-processing in a smart way, which I'll mention later. And variational quantum algorithms is, for example, the variational quantum eigensolver, the quantum approximation optimization algorithm, also known as QAOA. So these are all algorithms in which you sort of hope for the best. So you take a circuit and you run it, then you optimize it and you hope for the best that it will solve. I'm personally not very fond of, although this is a very interesting research field, there is a lot of limitations because you don't know really if the quantum circuit, it's really hard to find the correct quantum circuit. So you sort of make the problem harder. You first need to be able to run the quantum circuit, and also there is you also need to find the right quantum circuit. So this is, even more complicated. It's like a complicated square. Okay, so that was part number 1. So I don't know if there are questions or if it was all clear, too easy, too hard.
Is there any questions? I think none at this stage.
No. Okay. Was it relevant? I mean, to what you're discussing in the conference, in the workshop?
Yes, very much. It checks all the boxes almost. So, but I think people maybe are quite experienced with these things, or like they're familiar. Maybe they don't
Okay.
have any doubts. Yes, correct.
Okay, great. Okay, good. So now after this overview about the current state of quantum computing, I would like now to tell you about quantum simulations. So let's come back to the table that we had before. I said you can either try to use a quantum computer to solve a classical problem or a quantum problem. I mentioned already random quantum circuits, and now I would like to focus on quantum physics or quantum chemistry, which means to use a quantum computer to simulate a physical effect. So the idea is, as you all know, a very old idea by Richard Feynman, who said, well, if I try to simulate a quantum process using classical equations, I will run into a problem. And the reason is, these complex numbers that we were talking, or these exponential size of the Hilbert space, they are all, different aspects of the same problem. So that's why he said, well, maybe if I have a quantum problem, I should use a quantum system to solve the quantum problem. And maybe another quantum system is just a quantum computer that follows the rules of the game. So that's how quantum simulations were born. This is a field that has been very active in the past 20 years or even more, maybe 30 years. And started with the world of ultra-cold atoms. Okay, so let me echo. Actually, yes, I have a slide about general quantum simulation. So imagine you have a quantum problem. Quantum problem could be to understand the behavior of a molecule, or to know the quantum properties of a material, let's say the conductivity or the color of a material. Here you see graphene as an example. And let's assume that you have n size. As I mentioned, if you want to simulate classically, then you will need 2 to the n complex numbers. And already for n equals to 30 is 1 gigabyte, which is maybe sort of okay. You can work with matrix, with vectors of the size of a gigabyte, but it's enough to go to 40, which is already a terabyte, or 50, and it's just no too complex for any current state-of-the-art classical computer to be solved. So what do you do? Well, one solution is to enhance your classical computational capabilities. Before we mentioned, earlier on we mentioned a work with that used 1400 GPUs in parallel, or maybe the Summit supercomputer or any other supercomputer. So that will allow you to to increase this number maybe from 30 to maybe 40. So you can try to analyze larger and larger systems. But at the end, you will end up let's think of a molecule. So maybe you can analyze a molecule with 40 orbitals, which is usually a relatively small molecule. If you have a big molecule and with many electrons, with many orbitals that are playing a role, the problem will become intractable. So you can do an approximation. That's what we usually do, right? As physicists, we spend our time mostly on approximations. We can't solve the original model, so we solve it with a simple model. It is maybe midfield approximation, maybe a path integral approximation, maybe a large n approximation, all sort of approximations that we've developed so far. But, and yeah, that's what Feynman said. If I try my best to make the equations look as near as possible to what would be imitable by classical probabilistic computer, I get into trouble. That's the idea. So that's the problem. So the solution is, well, then let's use quantum computers. So I mentioned ultra-cold atoms that already they have been working on these type of quantum simulations for a long time. Here you see an example of what is known as a optical lattice. So the idea here is to mimic the motion of electrons using atoms. So instead of having electrons that move in a material, you have atoms that move in a potential that is created by the laser. So of course the scale are very different, and this is actually advantageous because electrons, one of the main problems with electrons is that they're very, very fast. So the energy scales are very large, so the dynamics is very, very fast. It's really hard to follow. In these ultra-cold atoms, the energies are much lower, and so the time scales are much longer. So it's much easier to study the dynamics of a quantum problem using ultra-cold atoms that mimic the behavior of electrons in a real material. But Nowadays, and that's what we are, the topic I would like to tell you today, is actually to use a quantum computer. Well, I mean, ultra-cold atoms are also by themselves. You can think of them as a computer, as a quantum computer, but here I really refer to universal quantum computers. So let's think of universal quantum computers that can apply any programmable gate, and then let's program those gates so that we can simulate an interesting non-equilibrium dynamics. And I would like to give you 3 examples. The 3 examples are different because, first of all, from the last year. They are all examples from the last year. They come from different platforms. So this is also a way to explore a little bit the different so-called modalities of quantum computer, different ways to build a quantum computer. And also I would like to highlight, a few tricks that were used in order to obtain a result on those noisy quantum computers. In theory, theoretically, to explore physics, we would like to have a system that is in the thermodynamic limit, so with an infinite number of degrees of freedom. But then, as we mentioned, in quantum computers, we are already restricted to small systems. So how you bridge that gap? And I will show you some tricks that maybe you can use also in your scientific work. So the example number 1 is from the group of MIT and Harvard. They are they're developing a neutral atom quantum computing. There is a company called QERA that sort of collaborates with them for building a quantum computer using neutral atoms that are trapped in an optical tweezer. So an optical tweezer is a very interesting physical phenomenon in which you use a laser light to actually trap an atom, and you can use it as a tweezer to take every individual atom and place it at will. So these quantum computers they are in vacuum. They take an atom, and then when they want it, so the atom has an internal degree of freedom, which could be, you could just think of it as 0 and 1. So the ground state and an excited state of an atom. So if the electron is the ground state, is 0. When it is in the excited, it is 1. That's one option, and if you consider a very highly excited state, it's called the Rydberg state. So these are also called Rydberg atoms. It just means that these are just neutral atoms that you excite to some excited state using lasers. And then when you want to make them interact, you just take 2 atoms and physically bring them close to each other. And when they are close to each other, they interact, and that interaction is your gate. So it's really like a Lego game. You take atoms and move them around and then place them one next to each other. So shuffling, moving them in space, and then a ZZ gate. So the ZZ gate is something that is created when 2 atoms are next to each other. Now, because these atoms can move, you can actually create an arbitrary geometry, right? You just place your atoms where you will. So even in 2D or even in 3D, so you can, unlike a material, right? In material has a very well-defined structure, right? If you give me some material, then you know that the atoms are placed in a very specific way, right? In a lattice. But here, because you can move each atom, you can control each atom, they are neutral atoms, they can control them, you can create a very arbitrary geometry. So here you see, how it looks like. This is just an optical table, an impressive optical table with many, many, many lasers. Of course, you need many lasers if you want to control many atoms. There are more details, but definitely you need to be able to use very focused and controllable lasers. You don't need 1 laser per atom. There are other ways to do it. Okay, so what they do, what they considered is a specific model. It's called the honeycomb lattice. Actually, it was studied, in a particular model. So this is called the Kitaev-Hamiltonian model on a honeycomb lattice. So on a honeycomb lattice is actually a lattice that is made of hexagons, next to each other. This is the name of the lattice. And again, in reality, there are not many materials that have this particular shape. But in an experiment like this one, you can just take your atoms and place them at will into so it's a 2-dimensional lattice. That's the honeycomb lattice. The Kitaev-Hamiltonian means that you have specific interactions between different neighbors. So In fact, depending of whether you're considering two neighbors that are on the horizontal or diagonal direction, so like this atom have some interaction. That's the red. This is XX. The orange would be YY, and the blue would be ZZ. So each atom interacts with the neighbors, right? Each atom has three neighbors. So each atom interacts with the neighbors, with each three of the neighbors, either with XX, YY, or ZZ. Actually, depending on which one, right? XX, YY, or ZZ. What's special about this model is that, and that's what the smart move of Kitaev is, that one can map it to a model of fermions. Actually, the models of fermions that comes out is a model of free fermions. So free Majorana fermions. So free Majorana fermions is something that we know how to solve. So in a sense, this model is very complicated when you write it like this in terms of the spins. Looks like something very unnatural, certainly very difficult to realize in a real material, right? In reality, I mean, in real material, why would these two atoms interact with XX, this YY, and this is ZZ? It's very hard to imagine. But in a simulator, it's easier. And in theory, it's even easier. So this is a model that theoretically is very well understood. And in particular, it has, as we'll see, two possible phases, depending on the behavior of these free fermions, whether the free fermions are bound in pairs or, if they can move freely. So in order to study quantum phase transitions, we need to be able to study the ground state properties of the Hamiltonian. As you know, quantum phase transitions are zero temperature phase transitions, so are related to the ground state of this Hamiltonian. So we would like to prepare the ground state of this Hamiltonian. And that's something that in a real material, if you want to prepare the ground state, you take the material, you cool it down, right? You put it in a fridge, a very good fridge, you cool it down, and then it will reach the ground state. But here, this is a simulator. You cannot cool it down. I mean, you cannot. There is no heat path. Maybe you can realize this Hamiltonian. So how do you create the ground state? And the way they used is actually in this case they were able to use ancillas in order to prepare the ground state. So they were able to okay, what you see here is the phase diagram. The phase diagram has three parameters, right? Jx, Jy, and Jz, and this is shown schematically here. So there are 4 different phases, and what they did, they actually started in this blue point. So they started by preparing the ground state of this specific Hamiltonian, which is the Hamiltonian in which Jz equals to 1. And they were able to do it using they were able to do it using ancillas. So they used 72 data qubits, so 72 spins, plus 32 ancillas. And the ancillas are actually those that enable them to prepare the ground state of this particular Hamiltonian. Okay, so this is one parameter. This is one point in the parameter space. How do you move to different parameter space? If I change the parameters, right? If I change Jx, Jy, and Jz, then of course the ground state will change. So how do I prepare my system? So what they did is they moved across phase boundaries using an adiabatic protocol. As you know, if you change the Hamiltonian slowly, the ground state follows you, right? If you take an Hamiltonian, and if you take a system and prepare it in the ground state of some Hamiltonian, and you change the Hamiltonian, that's called the adiabatic protocol, then the ground state will follow. And that's what you are trying to do. So, but, so that's called the adiabatic protocol. But now, this is not just any adiabatic protocol, it's the digitalized adiabatic protocol. What does it mean? It means that when I'm telling you that you are starting with Hamiltonian and changing it. But in a computer, everything needs to be done in a digital way, right? There are gates. You don't know how to apply. You cannot slowly change the Hamiltonian. You need to apply one gate after the other. So you need this move that you need to know. You need to move your Hamiltonian. You need to slowly change the Hamiltonian from here to here, for example, or from here to here, or from here to any other point. You will do it not smoothly, right, around this phase. You're actually going to do it in a digital way, so in a discretized way. So you basically, you will start with this Hamiltonian, then you change to this one, then you change to this one, and every time you change the Hamiltonian, there is a step. So you're applying here a step. And in this case, what they applied is actually 6 layers of okay. To make it really adiabatic, you would like to do very, very, very slowly. So let's say when going from here to here, you would like to have, like, I don't know, 1,000,000 steps. Then you are perfectly adiabatic. In reality, it's not 1,000,000 steps. They are using 6 steps. Okay, so that's already something significant. And the number of gates they need to apply is not terrible. I mean, you have 36 gates for the pairs, the right number of pairs, times for the lattice that they had, times 6 steps. So it's about 100 gates. You remember when we had the number we had before, I told you that for typical quantum computers, let's say I said if epsilon is 0.2%, the number of gates is 250. And this is, you see, this is about this number. So you are limited to about 200 gates or so. So let me show you one result. So the result was following. As I mentioned, the phase diagram has different phases, and the way to distinguish between them is to use the Chern number. So these are not irregular phases, these are topological phases. And the way to distinguish them is using a non-local order parameter known as the Chern number. And what they said is, look, when I start in the blue dot here, the Chern number is 0. This is the blue, light blue. If I move to the dark blue, well, then the Chern number is still 0. And when I move to the gray, the Chern number jumps to 1. So in principle, this is like, wow, it's amazing. I mean, the Chern number is going in, that's the idea of phase transition, something very sharp that happens. So the Chern number is always integer by definition. So it's either 0 or 1. You see that here it goes from 0 to 1. But actually, notice that there is something funny about this plot, that it doesn't have error bars. And the reason it doesn't have error bar, that actually, how did they obtain this result? How did they measure the Chern number? They didn't measure the Chern number directly. So what they did something else. They measured, they took the state. So they took the light blue state, dark blue state, and gray state. And they measured also two observables, XX, YY. So XX means that you take 2 qubits and you measure the expectation of the 2 qubits. YY, this is ZZ, and so on. So here you measure YZX. So you measure, Y on 1 qubit, Z on another, and X on a third one. These are all sort of things that you measure. What you see in this plot is the experiment, the theoretical ideal, and the theoretical wave noise. Okay, so now remember that the jump, okay, the phase transition occurs between the between these A-Z parallel and B. So it really happens between A-Z parallel. So between this point and this point. So the phase transition really occurs from this point to the other one. Okay, so the first 2 plots are in the same phase, the third plot in a different phase. Now, when you look at these figures, they actually look very similar. I mean, you see that the difference between this plot and this one is not, I don't know, it's quantitative, but not qualitative, right? These two are a little bit higher. Okay, yes, the third one is even higher. Then the fourth one is small. So they're really, I mean, the 2 plots are different. And the question is, how do they know that this has Chern number 0 and this has Chern number 1? And if you read the paper, it's actually a little bit hard to understand, but you need to go to the appendix. In the appendix, you will see that, in fact, the Chern number is evaluated using the learned parent Hamiltonians, assuming free fermions. In other words, what they did, they said, well, let's assume that this is a model of free fermions, and let's ask ourselves whether the best fit is given by a model of free fermions with 0 Chern number over a model of free fermions with Chern number 1. So they are not by any means, they are not measuring the Chern numbers, but they are trying to restore what was the Chern number by assuming that the model itself is a model of free fermions. Okay, you see, so they are already implicitly using an implicit assumption of the model to represent the result. So that's something. It's a trick, but I think it's a useful trick, right? Eventually, the paper was published. People liked it. So, sometimes when you try to write directly on a quantum computer, the results are not very convincing. You need to find a way how to present your result. Okay. example number 2. Let me actually take 1 minute break, and I'll be back. So,
okay.
Let me take a couple of minutes break, and then we'll go on with example 2 or
That's
3. In the meantime, if you have questions, think about the questions. Okay, so I'll see you back in 2 minutes. Okay. Yeah, I'm back. Sorry for the interruption. Okay, so any questions about the example 1?
So is there any questions? Anyone?
Hello.
Yes.
I
Yes.
have a question. What
Okay.
is the phase difference between these 2 phases you mentioned in the previous example?
Yeah.
What is the yeah. I do see that the string magnitude is roughly half, less than half for the first one, and then close to 1, namely 0.8 or something. Is that the way one differentiates them, or?
Okay. Yes. So what I was trying to say is that so the real difference is the Chern number, but the Chern number, if you try to express it in terms of the spins, this would be it's something really, really terrible. I mean, something that it's basically a product of all the spins together. So you cannot really probe it in the experiment. Then what they did, they realized they just asked themselves, what is the model that fits the best? So they considered an average over all these. So they considered all these data points, all these experimentally probed measures, and it's not obvious to know which one mattered most. So I don't know to tell. No one knows to tell you whether what made the difference. For instance, was the fact that I don't know. Maybe these two are high and high here and low there. It's not clear. I mean, what they did, they just took the data. It's really sort of a little bit like data, big data analysis. So you take those numbers and you plug it into a model and you check which one best fits the best. And there is not really a physical understanding of why this was lower or higher. So it's very non-generic. It's specific for the one they had. They said, well, I'm assuming that it's a free fermion model. Free fermion model, by definition, can have Chern number 0 and 1. And then I ask myself whether it's a model with Chern number 0 or Chern number 1 that fits best. But they didn't show, the entire data of, how the models were different. So I think there is a lot of faith that we need to put into this result.
Got it. Yeah.
Yeah, thanks for the question. So
Is there any
But
other
one
question?
needs to be realistic, right? You cannot measure the Chern number. This is also, it's a topological quantity. That's the main idea. You cannot measure topology by having local probes. So,
Okay. Is there any
okay,
other
good.
question? I think no. So you can please continue.
Okay, thanks. So, okay, the example number 2 is actually, these are the authors, is actually was performed on a quantum computer by IBM. So unlike the previous work in which they had access to a special, system that is available that was built and is available by the research group, here it's a work that used the quantum computers on the cloud. So just the quantum computers that you can find online. The epsilon in this case is 0.2%. As we mentioned, it will means that it will be able to perform something like 250 gates, a few hundreds of gates, and the number of qubits was 40. Okay, that's how it looks like from the outside. What is the key ingredient? So the model that they realized is actually a one-dimensional model. You see, it's a model in which each spin is coupled to the next one, so Si plus 1. And the coupling, it has two components, a ZZ component and an XX and YY component. So in this case, all the components live together. And depending on epsilon, it's either a ZZ ferromagnet or an XY model. So there is a phase transition as a function of epsilon. Okay, good. So what did they do? They also, as always, you have this problem of creating the ground state. So in this case, they created their ground state variationally. So they applied some gates, and tried to approach as much as possible the ground state of this Hamiltonian. So this initial state, ground state preparation, okay, this is what is shown here. So you have an initial state, which is just 0, 0, 0. And then you have some gates that you apply, which are variational gates, which means that you don't know a priori which gates you need to apply, but you optimize over the parameters of these gates. And you find the one that brings you closest to the Hamiltonian, closest to the ground state of this Hamiltonian. Okay. Then what they were aiming to probe is the Green's function. So the Green's function is just a 2-point correlation function. So it's the correlation between the qubit at point I and the qubit at point J. And how they do it? What they did is that at some point, so first of all, they start in the initial state, prepare the ground state variationally, then at some point apply a perturbation, a local perturbation. Next, they let the system evolve for some time, and finally they measure. So if you apply perturbation at point J and measure at point I, you will get the Green's function. You see the Green's function Ij, so the Green's function where the perturbation was at J and you measure at point I, and T is the time that occurred between the two times. So the Green's function is the correlation function between two spins at different times. So I and J is the point where you measured, sorry, the point where you perturbed, the point where you measured, and T is the delay time. And you can vary those parameters. So this is how it looks like in real time. So here in these graphs, what you see in the x-axis are the qubits. So the perturbation was performed in the middle. This is a one-dimensional chain, so you perform the perturbation in the middle. And this is, this blue dot. And you let it evolve with time. And what you see here is the typical light cone effect. So light cone effect means that when you put a perturbation at some point, the perturbation will evolve over time to different neighbors, from neighbors in sides until to the left and to the right. And you see a comparison between the result obtained with matrix product states and on the IBM quantum computer. For a model, okay, so this is for a model that models this material. So the parameters of the material were chosen to model this particular material, which is a one-dimensional antiferromagnet. Now, what you can do, you can take this data and Fourier transform it. So instead of having space and time,
constant perturbation applied. Is the perturbation constant in time?
Can you repeat?
Is the perturbation constant in time?
No. The perturbation is done at one point. So basically, you take a spin and you flip it. Think of just taking a single spin in some point and flipping it. Then you evolve. The evolution in time is done with a constant Hamiltonian that is uniform in space. So there is a local perturbation at some point time t, and then the time evolution is uniform in space. Okay? That's why where you see that the perturbation the perturbation at the beginning is only at a specific place, but then it evolves over the entire lattice and vanishes. There is no. If you had a constant in time perturbation, you would see maybe like a vertical line, right? A perturbation that is vertical. But here you see that the perturbation is only at time equals to 0. And then, the effect of the perturbation are felt. It's like a wave, right? This is like wave propagation. So it's like, I don't know, knocking on a table, and then there is a wave that propagates around you. So this is what you see here. That there is a local perturbation in the beginning, and then the waves that propagate to the right or to the left. So what you can do, you can analyze this figure in space and time by just applying Fourier transform. So you may imagine this as a two-dimensional plot. You do a Fourier transform in both axes, and you obtain a colorful plot like this one. And here, what is beautiful is that you can actually compare it not only with the experiment and the simulation. Okay, so this is the experiment and this is the simulation, the matrix plot state simulation. You can also compare it with an experiment. So the experiment is performed by measuring the response of the response of the material to different waves. Basically, it's the absorption, right? This is basically the absorption of waves at different momentum and frequency, which was done in the experiment. So it's called this is known as the structure factor of the material. It's basically the absorption of the material of spin waves with a given momentum and frequency. And so this is just a physical experiment on the material, which can be compared with either the simulator or the quantum computer itself. And you see what you should what you should see here. These are like lines. So this is basically the dispersion relation of the waves that propagate into the material, right? The omega of k, the dispersion relation of the material. Okay, so this is really nice because it can be related then to an experiment on a quantum system. Of course, maybe the limitation was that, yes, you could do it on a quantum computer, but you could also do it on a classical computer, so that you could simulate the problem on a classical computer. And that's related to the fact that the material is 1D, and in one dimension, we have very powerful numerical methods to solve these models. Okay, example number 3. So this is an experiment.
Emanuele, I have a question before you go to that example. See, I'm just curious to know what was the ground state they started.
So they start in the ground state of the Heisenberg. So you have this XXZ Hamiltonian, and they started as close as possible to the ground state of this Hamiltonian.
So the antiferromagnet would imagine that this would be very strongly correlated, isn't it?
So, well, I guess it depends on the value of on the value of epsilon.
Okay.
I think that epsilon in this material is not too big, right? If epsilon was 0, then the antiferromagnet it's so what you're saying is correct for epsilon equals to 1, right? In the Heisenberg Hamiltonian, but I think that the experiment was performed in an epsilon that is. This material has epsilon that is small, so that you are in the antiferromagnetic phase, which is just a phase in which the spins are up, down, up, down. So it's not. There are correlations, but it's not a topological. Anyway, this would be a spin half Hamiltonian. So yeah.
Okay. Thanks.
Yeah. Okay. Thanks. Yeah. Thanks for the question. Okay. So. This is an experiment that was performed on a different platform by Quantinum. So this is a platform that uses trapped ions. Actually, this is the platform that for now is showing the best fidelities. In these models, the epsilon is as low as 0.06%. So it's really, really very small. And if you use the sort of thumb rule that I told you before, it means that you can apply about 1,000 gates before you sort of lose your signal. Remember this 1/2 epsilon. That would be the number of gates that you can apply. Okay, so what is the model that were implemented? They actually implemented a two-dimensional transverse field Ising model. So that's a model that has ZZ interaction and magnetic fields. Importantly, this is the digitalized or Floquet two-dimensional transverse field Ising model. What does it mean? It means that in principle, you would like to apply at the same time both the coupling, ZZ coupling, and the transverse field, right? That's transverse field Ising model. But in a quantum computer, you cannot apply simultaneously more than one gate on a single ion. You can apply, gates on different ions at the same time. That's fine, but not the same. So the way you realize it in practice is by using. So this is how what is shown here. So you have these green dots. So the time is in the x-axis, and the different lines are the qubits. So the green dots means that you applied a single qubit gate. So that's the X gate, and then the blue, these two blue dots are the ZZ gate. So, but then what you see is that you also need to, each ion is connected to four different ions in a two-dimensional lattice. So let's focus on this ion here. So you need to first apply a gate with the upper ion, then with the lower ion, then with the left ion, then with the right ion. So you do it iteratively. You start with you apply first a gate on the ion, then you connect to the upper, lower, left, right, and then you apply again a qubit, and you do it recursively. Many times, so as much as possible. So in this case, what they considered is a lattice that has 7 × 8, so 56 qubits, and they implemented 20 steps, which means that they essentially had about, and each step you see there are many gates, so they had about 4,000 gates. This was the depth that they came upon. You see that this 4,000 is much larger than the number I gave you before. I said, well, I would give an estimate of 1,000 gates. Here they implemented 4,000 gates, but they use a trick, which I'll show you in a moment, which is known as error mitigation. So error mitigation is it's a set of techniques that allow you, in general, to trade more circuits for better performance. So instead of just running the circuit and measuring, you perform many circuits, and then you average over those results. So so in particular, the mitigation method that they use is called the zero noise extrapolation. What does it mean, zero noise extrapolation? So zero noise extrapolation is a method in which you would do the following. Let's assume you have a system with a given amount of noise. So that's 1. So here on the x-axis, I'm showing you the value of the noise. And the noise at the beginning is 1. So what you do, you actually artificially amplify the noise, which sounds like a very bad idea. And you see that when you amplify the noise, the signal goes down. Okay, so let's assume that the signal without noise would be 0, would be 1. Okay, so in the x-axis you have the noise, and on the y-axis you have the true value. So without noise, the true value would be 1. Well, you don't know how to be here, right? You don't know how to, you don't have that point. You have the point here, which is at noise level 1. So noise level 1, the physical observables is only 90%. You don't know how to reduce the noise. What you do know is how to increase the noise. And as expected, when you increase the noise, the value goes down. So if at the beginning was 90%, when you will say have increased the noise by 10 times, the value of the observable went to 50 down. So you're like making your system worse. But then the idea of zero noise extrapolation is that if you have many points in which you increase the noise, if you know what happens when you increase the noise, you can try to extrapolate. You see here, this is a little bit tiny. I hope you see it on your screen. You see these points are dashed. So on the right-hand side, you're increasing noise. There's something you can measure. On the going to zero noise is an extrapolation. So you're trying to do a fit I don't know, you do maybe an exponential fit or other types of fit, and then you try to extrapolate towards zero fit. One more point I need to highlight is that in order to apply this, how do you amplify the noise? And the way to amplify the noise is by, first of all, characterizing the noise. So you need to calibrate and know exactly which type of noise you have in your system. Then what you do, you add to your system specific gates that play the role of the noise. So you model the noise. What does it mean, noise? Noise basically means that your system, instead of doing what you're expected to do, it randomly adds some gates. That's what noise does for you. And what you do, in order to increase the noise, you actually add more gates. You add more noise to the system. So you really run more quantum circuit. You don't just run the same quantum circuit many times. You run the quantum circuit with additional noise many times. And then you try to extrapolate towards zero. That's the idea. So by doing this, you can increase, you can basically go deeper. You can simulate systems that go beyond the thumb rule that I told you. Right? If the thumb rule would give you 1/2 epsilon, would say be 1,000, here you can get up to 4,000 gates. So don't think that error mitigation is magic. It will not allow you to, if you have a system that was able to perform, I don't know, 100 gates, you will not be able to perform 100,000 gates. You can perform a little bit more. So if you see that with noise the signal was 90%, then you can improve it to 100%. So it gives you some improvement, but it's not create a signal that it was not there to begin with. What I like about this work is that it was also performed. They also performed a comparison with state-of-the-art numerics, and here you see an example. So what I'm showing you here is a quantity that they observe. So they defined a specific quantity, which is the total z square. So you just count the magnetization of the entire system, and then you square it, and you get a number. And what in the x-axis you have time. So times means the steps. Okay, these are known as drop test steps or discrete steps. So as I told you, they went until 20 time steps. What we see in the dots are the data points. So the blue dots are, for example, the data points of the experiment. The green dots is NA, which means noise amplification. So blue is what you do in the quantum computer itself to begin with. Green means the quantum computer plus noise. Okay, that's the maximum amount of noise they put. You see that it kills the signal. So it's something, it's not a good idea. You just put more noise, the signal goes down. But then you can perform the zero noise extrapolation. So the zero noise extrapolation is what you have seen here, what allows you to go from 1 back to 0. And here you see in the blue, when you do the zero noise extrapolation, you obtain these purple dots. And the purple dots have error bars because the extrapolation is prone to error. So there are error bars. So the purple dots is the best you can get from the error mitigation. And this is compared with numerics. So the numerics are these continuous lines, and the numerics is based on also matrix product state, which has a parameter that is basically the size of your simulation system, and they go from size 256 to 4,000, which is really a huge number. I mean, to do this simulation, you really, really need a very high performance computer, a supercomputer. And then you can also extrapolate also here. So you see you have all these colors, and you extrapolate them to this purple line. And you see beautiful agreement between the line, the purple line, and the dots. So the theory and the experiment are, the numerics and the experiment are one on top of the other. This was for a specific initial condition, which was like an easy initial condition. When they instead considered a harder initial condition, you see that the quantum system still converges. I mean, you see that you have these dots that make sense, while the numerics, you see that diverges. The numerics would even, at some point, the numerics even give you a negative number. When you extrapolate, you see that in the numerics, when you increase psi, which is this approximation number for the numerics, there is a huge variation, which means that it has not converged. Here you see that on the left, you see that when you change Xi, so you take larger and larger, better and better numerical precision, the change is small, becomes smaller. Here instead, when you take better precision, the change is very big until, and in some regime, it would even, if you try to extrapolate, you just get the wrong result. So that's telling you that we are in a situation where the quantum computer is already performing a quantum simulation that is comparable or maybe even better than the best classical available solutions. Of course, maybe, this is a very recent work. It could be that maybe someone will come with a better improved classical methods and will get better results. But this is what was presented here in this paper. There are many more examples. I mean, I think the field of quantum simulation is very broad. Google have been very creative in in selling their work, speaking about time crystal, quantum wormhole, and that people got scared that the quantum wormhole will it's like maybe a black hole and will destroy our universe. But then to them I say, don't worry, this is just a quantum simulation. And well, these are works that I've mentioned. Sorry, this is another work also on Foucault topological phases. And this is a work about quantum chaos. This is one of my last slides. It's about work that we've done in our group, where we studied quantum simulations of small systems. So we focus really on systems with up to 6 qubits. And nevertheless, we were able to demonstrate interesting effects, including topology, non-locality, quantum phases of matter, questions about the state encoding. So how you prepare a state? What is the best way to prepare a state variationally? And also we have a work with actually, this is a collaboration with an Indian colleague, and we did quantum error detection. So detection is the first stage toward quantum error correction. And we asked how we can use specific quantum states called the cluster state to perform, to detect specific errors. It's nice. I mean, this is also an implementation of an IBM quantum computer. And yeah, so in these works, you can look at them up. We did some theory, and we also demonstrated how this works on a real quantum computer by different companies. So okay, conclusion. So I think the main message I would like to deliver today for this workshop is that quantum simulations are possible. There are different platforms with different properties. Of course, the number of qubits is one parameter that you should look at, but you should also look at the fidelity. And I try to give you this thumb rule that the number of gates that you can simulate is about 1/2 epsilon, where epsilon is the error per gate. So if your error per gate is 0.1% or 0.2% or so, you will be able to usually run between 100 and 1,000 qubits. And you can maybe increase that if you use noise mitigation. So you can reach up to several thousand gates for state-of-the-art quantum computers. I also highlighted tricks or things you need to take into account when you perform a quantum simulation. First of all, how do I prepare the state? Do you want to use a variational circuit? Can you use ancillas? Ancillas are useful for preparing specific ground states of integrable models. What are the gates? The models that I told you about were mostly the Ising model or nearest neighbor models. So you need to think ahead of time whether the model you have in mind, what is the topology, what is the lattice that you're using that is compatible with the platform that you're using. So it's very important to know which platforms you plan to use before you think about the Hamiltonian you want to simulate. Is it 1D, 2D? What is the connectivity? And the third point I mentioned is the fact that in general, quantum simulations that are based on that work on gate-based quantum computers really require to digitalize the dynamics. So if you need to simulate a Hamiltonian dynamics, you want to probably break it down to flow-chaos, to step-by-step dynamics. Okay, yeah. So let me just conclude. Let me just conclude with this slide where we have some QR codes. Also, I would like you to attend to 2 events that we are organizing at Kernel, and you can see all the information at kernel.org. So we have a webinar about quantum simulations in 2 weeks, in July 16, which is an Italy-Israeli collaboration. Of course, everyone is welcome to attend. It's just funded by the Embassy of Italy in Israel. And it's shorter, it's just a couple of hours. We'll have different speakers about topics of quantum simulation, including one of my former students, who is now Matan Ben-Dov, who now works at Kedma, a startup in Israel that deals with error mitigation. So there is the company that is trying to make error mitigation into a business. And if you want to learn more, please come to this webinar. And we also have an in-person conference. So I'm not sure if any of you have been in Israel before, but I really welcome to check out, again, on the website of Kernel, all the information about an in-person meeting. We also have the possibility to submit contributed talks from students and postdocs or researchers. And it's going to be in February 2027, not far from, in Israel, not far from Jerusalem, in a beautiful place. So, yeah, so thank you for your attention.
Yes, thanks a lot, Professor Dalla Torre. So, is there any questions from the audience?
Yeah.
Yes.
So, suppose you are given an opportunity to work with the quantum computer. Which one would you prefer the most? The system with superconducting qubits or Rydberg atoms, or the other one?
Okay, so I think that I think the 3 parameters. So the answer is depends on what you are trying to do, and the parameters you need to take into account are twofold. On the one hand, the fidelity. So right now, the superconducting circuits have usually fidelity of about 20, an error rate of 0.2%, which is similar to the one by Rydberg atoms. Maybe Rydberg atoms a little bit higher. So in that sense, I think superconducting circuits are better. Trapped ions, especially trapped ions by Quantinuum, have a very low error rate of 0.1%, while other companies like IonQ have larger numbers. So that's one, the error rate. But the second parameter is a question of connectivity. So if you want to consider, let's say, a one-dimensional model, then you can use easily superconducting circuits, because you can just think, you have in superconducting circuits, the connectivity is fixed. Every qubit is connected to one or two maximum neighbors. So you know exactly, two or three neighbors. So the topology is fixed, the connectivity is fixed. If you, for instance, want to consider a square lattice, that's not usually possible on superconducting circuits. So then in this case, you would need to use other systems. The advantage of both ultracold atoms and neutral atoms and trapped ions is that you can set the connectivity, because they really physically move in space the ions or the atoms, and so that you can connect every atom to every ion. So that's the second parameter. The third parameter, which is the most obvious one, is the number of qubits. So right now, superconducting circuits have hundreds of qubits, while trapped ions and trapped ions and neutral atoms have usually in the tens of atoms. So there is a question. This is the question. Now, there is also another parameter, which is availability. For instance, right now, Quantinuum has the best quantum computer in terms of fidelities, and they have a significant number of atoms, but their fees are very high. So this is also a question. Will I be able to afford running on the Quantinuum? Now, if you cannot afford it, that's fine. Maybe you can you can work with a different platform and do something else. So I think it's really, I don't think there is one right. If you have a very well-defined, specific, especially commercial application in mind, then maybe I can give you a suggestion which is a clear cut. But in terms of basic science, we are much more open. Even if you're not running the state-of-the-art quantum computer, but you're running a smaller one, you can still do things that are interesting. I mean, I think if you are creative enough and you open enough to ideas, etc., you can do things that are interesting even with small qubits. I mean, the work that I've shown you before, these sort of many pictures that I had in a single slide that are our own work. In most cases, we use up to 6 qubits. So we didn't need to have access to the best quantum computer available. And yet, I think they were interesting. I mean, they were published in decent journals, some of them even in very, very good journals. And I think they were interesting from a basic science perspective. Okay, thanks, Raja.
Yeah, Kumar, I have a question.
Thank you so much for illuminating the session.
Emanuele, this is Prasanta here.
Oh, hi, Prasanta.
Hi. See, the question is, did you try to find out things like concurrence or discord, through antiferromagnetic systems or through simulations?
So we had a work going a little bit in this direction, which was studying quasi-probabilities. So essentially, there is a question of, if you have a quantum state, how much the quantum state is non-classical, right? That's one typical question that one would like to ask. And so we, in this work, is by Abbas Malik, who was a postdoc at Bar-Ilan, is now back in India. So we built like a small engine, a quantum engine, and we studied the energy flow. So basically, the thermodynamics of a small engine, and we demonstrated that we were able to break the classical limits of thermodynamics. Of course, okay, that's fine because it's a small system and it's quantum, so it doesn't need, we didn't break thermodynamics, but we were able to show, for instance, that we could create a backflow of energy from a cold bath to a hot bath. Again, it's a small system, so that's why this was possible. But then what we realized is that the state we obtained essentially could not be described using classical probabilities. So it was about studying quasi-probabilities. I think, other types of entanglement measures are also very interesting. And again, one needs to think creatively, and maybe focusing on small systems, one could obtain interesting results.
Okay, thank you. Very nice talk. Really enjoyed it. Thanks.
Is there any more questions?
Yes, I have 3 questions, so allow me to ask. Thank you for a very interesting and informative talk. My first question is, how effectively we can simulate Hamiltonians, which you mentioned in your slide, example 1 and example 2, by using tensor networks or matrix product states, and what kind of benefits one can leverage from that simulation?
So I think matrix product states usually work well for systems that are one-dimensional. If you have a more complex, like two-dimensional connectivity, it's harder. And I think there is a challenge, so in the past, there have been several papers that claim that, yes, the quantum computer can perform a quantum simulation that cannot be simulated by these classical matrix product states. So you usually want to benchmark the best quantum computer versus the best numerics, right? To show an advantage. That would be the idea. But in many cases, then people just show that a better implementation of the network of these matrix product states was able to reproduce these the quantum simulations. So
okay. Thank you. My second question regarding quantum error correction. So can we reduce or mitigate error correction, errors by using topological properties of qubit?
So yes, so indeed, I mean, the reason why people are so interested about these topological phases of matter is that they can be used. They can be used for quantum error correction. In reality, so far people were able to demonstrate how to realize maybe a single topological protected qubit. So I think the way before we actually can use those topological protected qubits to make a calculation is very far away. So for the moment, we can sort of demonstrate maybe, one small building blocks or a few of them, but having a topological, qubits used for a calculation, it's something that is still far away. That's why I focus here in my presentation about quantum error mitigation versus quantum error correction. Quantum error mitigation is something that is already available. Quantum error correction will be probably available much in the later future.
Thank you. My final question is in your slide related to example 3, one key result. On x-axis, you mentioned Trotter step. So does it mean that you use Trotterization algorithm? And if yes, then how do you identify truncation size of Hilbert space in your calculations?
Okay. Yes. Thanks. So you're right. So Trotterization simply means that if you want to, Trotterization is a method by which you take a continuous in time evolution, so e to the IHT, right, the evolution over time of a constant Hamiltonian, and you transform it into discrete steps. So there are different levels of Trotterization. In reality, what one usually does is just the lowest level. So if you have an Hamiltonian that is the sum of two terms, let's say a ZZ coupling and the transverse magnetic field, the lowest approximation is just to do ZZ, you just separate the two. So you first apply ZZ and then apply the transverse magnetic field. Now, theoretically, one can do better than that by analyzing higher order terms. So the Trotterization expansion is really like a Taylor expansion of some sort. So you can really think of higher order terms. In reality, the lowest order one is the one that works. So the Hamiltonian you just get, the Hamiltonian is a sum of two terms. So you first apply one term, then the other. That's it. You don't go to further orders. Just because then you would need to apply a very complicated gate. And while maybe this is beneficial for the Trotter expansion, it's very bad for the quantum simulation, the quantum computer, because you'll need more quantum gates.
So in that case, maybe we are losing some quantum effects if we are not considering higher orders in our Taylor expansion, or maybe I'm wrong.
Yes, but then the question is, I mean, the question it's a question of balance. I mean, you have you'll get a better simulation because you go to higher orders, but on the other hand, you'll get more noise, or you need more gates. So I think that resource-wise, you have limited resources in terms of number of gates. You probably prefer to work in lower order, but going maybe for having fewer gates is better than having many of them.
Thank you. Thank you.
Okay, I'm sharing. By the way, I'm sharing. I'm sharing here the work with Abbas about these quasi probabilities in and black flow of small quantum engines.